All right, percent error. It's our topic. How do we calculate percent error and why is it important? Well, first of all, if you get results and they're way off, you should know that. And maybe there's something you could do to improve and bring your percent error lower, right? Here are our objectives. Pause it if you really want to read them. All right, so we can find the formula for percent error on table T, which is the back of your reference tables. And here is the formula. Percent error is measured value minus accepted value over accepted value, and then times 100, because again, we're giving it as a percent. All right. A lot of times you will see this formula, not on this reference table, but including these straight vertical lines standing for absolute value, meaning percent error would only be recorded as a positive. However, based on this formula, it can be okay, measured versus accepted. Let's talk about it. Measured means it's from the lab experiment. Okay, so you actually did measure it. So you may have calculated the density, but it came from the mass you measured and the volume you measured. Okay, so it came from your lab experiment. And then the accepted value has to be given to you. So somebody has to tell you the right answer, or you can find it on table S. We can find all the densities on table S. Okay, so it can be something that's in your reference table, or you would have to be given the accepted value. So what about if it's positive or negative? So if you have a big measured value that's bigger than the accepted value, your percent error will be positive. If it's smaller, the percent error will be negative. Most often, the percent error is given as the absolute value. So say there's a question on the test, what's the percent error? You calculate it to be negative 9.3, but you don't see negative 9.3, but you do see 9.3%. That's going to be the right answer because most often it's represented as the absolute value. So let's do a practice problem. So in an experiment, you determine the density of aluminum to be 2.42 grams per centimeter cubed. Calculate the percent error. So remember, measured minus accepted divided by accepted times 100. So you're going to plug in the numbers. Where did I get that 2.70? From table S, I found the density of aluminum. So I'm going to do that subtraction first. Then I'm going to do the division. And remember, I can cross out those units. So I'm just left with a percent, 10.37%. Based on significant figures, which is coming up in a lesson, I want that to be 10.4%. Be careful. Sometimes the language of the problem can be confusing. The measured value is always what was done in the lab. It was from the experiment. The accepted value is always the right answer, what you're comparing it to. Okay, so a reaction between 1 mole of sodium and 1 mole of chloride should yield 42 grams of sodium chloride. In your experiment, the actual yield is 32.73 grams. Calculate the percent error. Here's where you have to be careful. So here's the formula, and people will read the word actual and say, oh, that's the right answer. No, that's from the experiment. So the measured value from the experiment, the should yield, that's the right answer. That's what you should have gotten. That's the accepted. Okay, so you do the subtraction, then you do the division, and significant figures. From my measurement, I don't count the, for my measurement, I need 4. So then I'm going to round. But again, we'll do significant figures later. And here's one more example. A student measures that a piece of string is 3.1 centimeters, but the actual length is 2.9 centimeters. What is the percent error? Again, the formula. So I measured, the 3.1 is what you measured, the actual length, right? That's the right answer. Do the subtraction, then the division, and my answer is 3.1%. So in class, we would do a quick review. Blue-kit, always fun. But that's it. So that's how to calculate percent error. Just a straightforward, simple process. And hopefully you learned something new today.